Welcome guys, Mr. Hyatt here. In this short video, we're going to discuss resonance. So resonance is the idea that we can draw many, or sometimes two or three different versions of Lewis structures that represent the same formula. So if you notice on this diagram right here, we've got two different versions of the same thing. It's still O3. There's still one double bond, but those double bonds are in different locations. So as we've talked many times, form controls function. So this molecule is electronegatively different from this molecule. The polarity is going to be different. The concentration of the negative charges is going to be different. So these molecules will function differently based on which version that we see. Let me move myself up here now. So you see we've got a ringed structure. We haven't gotten to ringed structures yet, but this would be multiple versions of the same molecule. If you notice, the double bonds are in different places. So if you notice here at the bottom, the true structure, when we determine this experimentally, the true structure is going to be something like an average. It's going to be sort of this, or sort of this, sort of this. And we'll see that the number of versions relates to how evenly distributed those versions are. So you can imagine if there are 3 resonance structures, they'll be about 33% each. If there are 2 resonance structures, they'll be about 50% each, unless one or the other is favorable or becomes more stable. So think about how our bonding rules might apply there. There's a really big idea that's called formal charge. Here is the sort of how we're going to figure out which of these resonance structures is the best. We're going to look at the difference between the number of valence electrons on the free atom versus how many assigned to the atom in the molecule. So we may need to draw a Lewis dot structure for oxygen, and then one for O3, and compare the formal charge on each individual element. So let me show you kind of what we'll do with that. The most stable structure has the smallest formal charge and the most negative formal charge on the most electronegative atom. So think about the periodic table and where electronegativity increases and decreases. So these are not real charges. These are representative. So here's an example. Let me move my face down here so you can see a little bit better. We've got 2 resonance structures for CO2. CO2 could form with 1 triple bond and 1 single bond, could form with 2 double bonds. If we count the number of electrons around each atom, all the octets are satisfied. So when we look at this version or this resonance structure, every atom has the same number of electrons that it would have in its base charge, or in its base by itself is what I'm getting at. And over here, the big issue that we have is that we have a negative charge on a less electronegative atom. Let me try that again. Bigger problem is that we have a larger negative charge on a less electronegative element. So that's not good. Since I did such a bad job here, let's try to define it. So formal charge of an atom is the charge that an atom would have if all the atoms had the same electronegativity. So where would those electrons go? Let me move my face again. To calculate it, we're going to take the valence electrons minus the number of bonds and lone pairs. So here is a practice. If we were to look at the Cn ion, that's not cyanide, that's C and N, we can take our valence number of electrons minus our number of bonds. So 4 valence on carbon, we've got 3 bonds here, we've got 2 free electrons, so we subtract all of those. Our formal charge on carbon is -1. Same thing for nitrogen. There are 5 valence electrons. We've got a triple bond shown here, so we subtract 3. We've got 2 free electrons, so we subtract those, and we get a formal charge of 0. So that should help us figure out if, this is only one version of this is only one resonance structure, but if we had two resonance structures, we could compare those formal charges, and that tells us which one should be the right resonance structure.